Okay, so welcome back everyone to the second episode of the season. It's my pleasure to announce or to introduce Sebastian Spindler, who will be talking to us about counting l-isogenies with different modular polynomials.
All right.
Sebastian, the floor is yours.
All right. Thank you very much for the introduction. So I will be talking about how to count l-isogenies with different types of modular polynomials, and we will focus on a few specific ones in this talk. This is based on joint work with Thomas den Hollander, Mark Huben, Søren Kleine, Matthieu Müller, and Daniel Slamanik. Some of the work is still in progress. All right, so to start, let's look at some motivation, namely the classical modular polynomial. I think probably most of the people in this call have seen this polynomial before and mainly know it's by the following property, saying that if we have two j-invariants over some field whose characteristic is not L, then these are l-isogenous, meaning there's an l-isogeny between representatives of this j-invariant, if and only if plugging them into this classical modular polynomial returns 0. But even if you know the polynomial by this property, you might wonder, well, where does this polynomial actually come from? How is it defined? Also, you might wonder, why is this actually true? Why do we know that this property holds? And the third question, which is, I guess, the kind of natural next step is, are there other polynomials like this in the sense that we can use them to detect l-isogenies? And in this talk, I mainly want to focus on the third question, but kind of already, by the way, I need to introduce some prerequisites. We will also cover the first two questions, at least to some extent. So to give you an overview of what we're going to talk about, we are going to start with a brief introduction to modular curves, and the emphasis here really is on brief. That way, naturally, we will get to the classical modular polynomial, how it's defined, where it has the properties that we want. And then we want to move on to other modular polynomials, but to make our life easier, and this will become clearer in the talk, we will introduce the resultant technique, as I like to call it, basically using resultants to prove some stuff about the other modular polynomials in an easier way than going into the modular picture. And then we will start looking at these other modular polynomials, namely the canonical, Atkin, and Weber modular polynomials. And finally, we will show an application, namely we'll look at isogeny proofs of knowledge using these different modular polynomials. So to start with modular curves, we need to understand elliptic curves over the complex numbers. And it is a well-known result that, of course, takes some time to prove or some effort to prove that elliptic curves correspond to quotients by two-dimensional lattices in the complex numbers. And this correspondence is made explicit via the following isomorphism, where you map the quotient of this lattice to the elliptic curve defined by this lattice via this Weierstrass P function and its derivative. And the other half of this correspondence is the statement that for every elliptic curve over the complex numbers, or at least up to isomorphism, we can always find a suitable lattice such that we have such an isomorphism to such a quotient. Importantly, this lattice view allows us to kind of work with a lot of complex analysis. And the first thing we can do is we can just take the lattice and rotate and stretch it a bit so that our basis is given by 1 and an element tau, where this tau is a complex number with imaginary part being positive, so in the upper half plane of the complex numbers. And this will be quite useful for what we will do next. Just as a small comment, we will abbreviate notation a bit, namely just writing e lambda tau as e tau and the j invariant of e tau just as j of tau. So now for modular curves, the main observation is that the group of 2 by 2 matrices with integer entries and determinant 1 acts on the half plane via the so-called Möbius transformations. So where you take the matrix A, B, C, D and act on tau by mapping it to A tau plus B over C tau plus D. And importantly, the j invariant is invariant under these transformations, meaning that if we plug in the image under such an action, then we get back the same j invariant as if we didn't apply the action before. Of course, because of this invariance, we can use the j invariant to define a function on the orbits under this action, meaning that since it's invariance under this orbits, it defines another well-defined function from this orbit set to the complex numbers. So to now get a curve, since we want to talk about modular curves, of course, what we need to do is we need to compactify the set of orbits because on the complex analytic side, this is a non-compact Riemann surface. So compactifying it will get us a compact Riemann surface in this case. And this will yield the modular curve x1, In this case, we actually only need to add 1 point, but that's neither here or there. And importantly, the j-invariant now on this curve defines a rational function. The nice thing, and that's why really the j-invariant is such an important thing from the view of modular theory, is that this is in a sense the universal modular function of this curve, meaning that, well, first of all, this curve is actually just a projective line, so it has genus 0. And any rational function on this projective curve can be expressed as a rational expression in this j-invariant function. So this is the, in a sense, most basic, but maybe also in the view of some, the most important modular curve that exists. But of course, we also want to look at other modular curves. And for this, we need to make a small interjection to these so-called congruent subgroups. For this, we take a natural number and we look at the surjective reduction map from the integer 2x2 matrices with determinant 1 to the 2x2 matrices with determinant 1, but with coefficients now in Z modulo n. And the kernel of this reduction map is the nth principal congruent subgroup gamma n. So explicitly, it is given by these integer 2x2 matrices that reduce modulo 1 entry-wise to the identity matrix. So this is the principal congruent subgroup, but of course, the name kind of suggests that there are other congruent subgroups. And indeed, any subgroup such that we can find some gamma n lying in there is called a congruent subgroup. And of course, now this gamma n lying in there may not be unique, or in fact, it will not be unique because there's a chain of them lying in there automatically once one is in there. But what we can still do is we can say the minimal n is the most interesting one. And this minimal n such that we find a gamma n inside the subgroup gamma is called the level of gamma. We will see in a second where this level actually comes into play with a concrete example. But for now, let's go back to our setting of the action. What we can do now is we can take any congruent subgroup in SL2Z, and we can again look at the set of orbits, and under a suitable choice of compactification, we obtain the modular curve x gamma. This can also be obtained by acting with this group gamma on the so-called extended upper half plane, and then the notion of cusps of the subgroup comes into play. But for us, the non-compactified part will be the most important anyway, so we won't go into more detail on that part. Now we have, of course, already seen an example of this, namely if we look at gamma 1, so this first principal congruent subgroup, then this is just a whole group SL2Z, and there we get the curve x1 back, which also kind of explains the notation x1 being just x gamma 1. The other main modular curve that will be of interest to us is the curve x0n, and this is the curve given by the group gamma 0n, unsurprisingly. And this subgroup, this LLN congruence group, is defined by all the matrices in SL2Z such that reducing them entry-wise, modulo n, gives us an upper triangular matrix. So where the bottom left entry is congruent to 0, modulo n. So this is a level n subgroup. And of course, the question is, why are we actually interested in the subgroup, or what does this actually tell us? So let's put some effort into understanding what the subgroup actually does. For this, what we can do is we can look at an n-torsion basis of our curve e tau, defined by some tau in the half plane. And let's say this is given by 2 points p and q. And we then take a matrix in this gamma 0n and just look what happens when we apply this matrix by a matrix vector multiplication to this vector p and q. Then, because the bottom left entry is divisible by n, it kills the point p. So what we get as a result is just ap plus bq and dq in the second component. So as long as we act with such matrices on this vector, we will always stay in the subgroup generated by q in the second component, while in the first component, more or less anything can happen. This is the reason why, when we vary over all possible bases of n-torsion and identify orbits according to this above law, one can deduce from this that the elements of this orbit set of gamma 0n, or of the half plane with respect to gamma 0n, correspond to isomorphism classes of elliptic curves together with this n-order subgroup, the cyclic n-order subgroup generated by Q that we see getting fixed in the second component under this above action. And of course, as isogenists, we know that a cyclic n-order subgroup is the same as a cyclic n-isogeny. So we have some relation to isogenies now, which is great. To not missed name cyclic a bunch of times, and also because we're mainly interested in prime degree isogenies anyway, I will for now assume that we are dealing with a prime, but essentially if you make the right adjustments, everything that I say will also transfer to non-prime isogenies. All right, so now that we understand this modular group, let's understand the curve belonging to it. So what we can do is we can forget this l-isogeny, so we can kind of get rid of this additional cyclic group or this additional group generated by a point of order L. And this is the same as just instead of looking at orbits under the gamma 0 L action, to instead look at orbits under the full SL2 set action, which of course bunches together a bunch of orbits. And doing this induces a degree L+1 map. So basically we take the L+1 different orbits and bunch them together into one orbit. From our x0L to x1. And since we are dealing with curves, we also have function fields, and there such a map corresponds just to an inclusion of the function fields the other way around. So we get a degree L+1 function field extension of the field generated by the j-invariant to the function field of this curve x0L, so this field of rational functions on x0L. So now we want to understand, well, how does the second function field actually look like? And for this, one observes that one can define another rational function on x0L, which is induced by just mapping tau to the j-invariant of L tau. And this corresponds to taking the target j-invariant of the l-isogeny given by the cyclic subgroup that classifies our orbits on the non-compactified part, of course. Now, this is another rational function, and in fact, similar to the x1 case, we actually have identified all rational functions with this. Namely, the rational function field of x0L is generated by just a j-invariant of tau and a j-invariant function of L tau. So we have these two j-invariants, so this is nice, and now we actually have everything set up to define the classical modular polynomial. But before that, one more comment on how to understand the statement in terms of isogenies. What this is essentially saying, since x0L or the non-compactified part of it is just to be understood as l-isogenies essentially, what this statement says of this equality of these function field is that l-isogenies are generically determined by their starting and target j-invariant. Of course, there are some pairs of j-invariants where you have multiple l-isogenies between them if they are l-isogenous. But in most cases, if there is an l-isogeny between them, then it is unique. And that is kind of captured in this equality of function fields here. So now we can define the classical modular polynomial. And this is relatively easy to define now. We just function field generated by j tau, which is just a function field of the curve x1. And this is the so-called classical modular polynomial. Now, what isn't obvious is that this classical modular polynomial actually has integer polynomial coefficients in j tau, meaning that if we consider it as a bivariate polynomial, then it actually just has integer coefficients. But this is, of course, a nice property, and this comes kind of down to the choice of modular functions that we make. And more than that, it's also a symmetric polynomial, which kind of follows from something we will look at later. And in each variable, its degree is just L+1, which, as you recall, is the degree of this function field extension. Now, having this modular polynomial, we want to understand the statement that I introduced earlier of these j-invariants being isogenous if and only if plugging them into this polynomial gives 0. And for this, we just need to understand the roots of this modular polynomial. And explicitly, these are given by taking the j L tau function. Of course, this needs to be a 0 by the fact that it's the minimal polynomial. But if we take a representative set of the left cosets of SL2Z over gamma 0L, these are L+1, of course, and we apply the action of them on j L tau, so precomposing by AI, then these will actually also be zeros. And because there are L+1 of them and the resulting polynomial given by these factors will actually be the right polynomial, we see that these are all the roots of our classical modular polynomial. Now again, in terms of isogenies, this representative set represents, or like these actions, these j-invariants that we get by acting on j L tau with these AI, these represent the j-invariants L isogenous to our j tau. Kind of just by definition of this classification, if you look back at this action by gamma 0n. And from this, we immediately obtain the statement that we saw earlier for the complex numbers at least. So if we have a prime L and two j-invariants in the complex numbers, then the number of l-isogenies from j0 to j1 is exactly the multiplicity of j1 as a root of the classical modular polynomial where we plug in j0 into the first component. And of course, this implies this weaker statement that I showed earlier, that the left side has non-zero cardinality if and only if the right side, on the right side, j1 is actually a root of phi l j0 chain. So we have this statement over the complex numbers, but of course, in cryptography, we're most interested in finite fields, or at least in positive characteristic. And it is well known that this also extends to positive characteristic. So explicitly, if we instead look at j-invariants over fp bar, where p is a prime that is not equal to L, then we have the same equality between the number of l-isogenies and the multiplicity of the root j1. But why is this actually true? The answer to this is, well, it's actually quite complicated, because the algebraic theory of these modular functions, with which we saw the statement over the complex numbers, this does not extend to positive characteristic. This shouldn't be too surprising, because we're basically doing a lot of complex analysis. So we're working with Eisenstein series and having some notion of convergence there. And all of these things get lost if we go to finite fields. So we don't have an algebraic theory of modular function, but what Igusa was able to show, he was able to develop a so-called geometric theory of modular functions in arbitrary characteristics. And he proved the existence of a suitable model of the level L modular function field that behaves well under the reduction mod P, assuming that P is not equal to L, or more generally, that it doesn't divide the index of the modular polynomial we are looking at. And admittedly, I don't know the full details of how this works exactly. I think there is some kind of deformation technique involved here. But what I want to say with this slide and all of this exposition here is that actually understanding why this works in positive characteristic is quite a bit more complicated than over the complex numbers. So what we will do in this talk is we will just work with this understanding of the classical modular polynomial as a base point. So basically, we want to relate all other modular polynomials back to the classical one. But now that we have looked at this classical modular polynomial, you might wonder, well, why are we actually interested in other modular polynomials? And in view of the examples we will look at, I can basically give two motivations. The first one being that if we look at the additional level structure, so basically this additional L torsion that we saw, that we obtain from these congruent subgroups, then this allows us a compactor representation of isogenies. And we will see this explicitly in a bit. And the other thing is kind of related to a third example of the Weber modular polynomial, which is just saying that certain level structures can be used to remove some, so if you want to call it that, redundant information of the j-invariant that basically isn't really that important. I will make this a bit clearer when we get to that example. So I hope this motivates us enough to look at other modular polynomials, but to do that, I want to introduce the technique I mentioned earlier, the so-called resultant technique, to make our lives a bit easier, as we will see in a bit. So to recall the resultant quickly, for two polynomials over some coefficient ring R, the resultant is an element of this coefficient ring. And at least if we're working over a field as a coefficient ring, then usually it's known by the property that this resultant is zero exactly when the two polynomials share a root once we go to the algebraic closure. So otherwise, you could say that the GCD of these two polynomials is of positive degree. And what we want to do now is we want to extend this a bit. And we can do this by looking at subresultants, or more so by kind of approaching them from a more arithmetic point of view. And we get the following statement. So we start with, again, two polynomials. Now, G is just another polynomial over a field, and H is a polynomial over a polynomial ring in a field. So a polynomial ring Kj as coefficients. And we take two such polynomials, and we take a point in the field K, such that when we evaluate the polynomial H at U with respect to this coefficient variable J, then this preserves the degree in the Y variable of our polynomial H. What we do then is we count the number of roots of our polynomial G, such that this HUY polynomial also vanishes at them. And here you might notice this kind of double bracket notation. And what I want to indicate by that is that we really count the set as a multiset. So if G has a root of multiplicity 3, for example, then we count the root 3 times. This is important for giving this precise statement that we have and that we also want to use later. Because what we can now deduce, having this count, is that the resultant with respect to y of these two polynomials g and h, which will now be an element in the polynomial ring kj, so this coefficient ring of h, this has a root of multiplicity at least this m that we counted at the point u that we specified at the start. And there is a small technicality here, because this multiplicity is characterized by derivatives. So we run into some technical issues if the characteristic of a field is smaller than the m. But for our setting, this will not really be relevant and kind of can be fixed by hand in a sense. I won't go into detail on how to do this, but if you have questions, I can on that, I can talk about that after the presentation. So this is, of course, quite technical. So let's maybe break this down to a more down-to-earth approach of what we want to do. So what we want to do is we want to find other modular polynomials. And the way we do this is we find other modular functions. Sometimes one suffices, sometimes we need more than one. And we want to look at the corresponding polynomial over the complex numbers. Then an important thing to transfer this to other characteristics is that we can actually reduce the coefficients. And for that, we want to make sure that this polynomial that we get actually has integer coefficients. Then once we have ensured this, we can understand via the modular theory how these polynomials that we obtain actually relate to l-isogenies over the complex numbers. And here we can really use the whole tools that we get from modular theory, the whole infinite products, infinite series, basically, and all these modular functions that we already know. But once we have achieved this understanding, what we do is we apply via a resultant equation some kind of understanding or some kind of technique to understand this polynomial and arbitrary characteristics. So we want to kind of reformulate this relation l-isogenies into such an equation, and somehow on the other side of that equation, we want to see the classical modular polynomial. And once we have achieved this, we can just profit from our resultant technique theorem, of course, modulo this understanding of the classical modular polynomial that I kind of gave as a base point. So again, this was still a bit abstract, but I wanted to kind of give you an idea of what our strategy will be. And now we will see the strategy applied to 3 examples. So the first example is the canonical modular polynomial. So for this, we look at the case where this curve x0l has genus 0, which means similar to the x1 setting, it's just a projective line, and its function field is generated by one single generator. So of course, looking at this case, we need to first understand when it actually happens. And this is the case, of course, once we have this one parameter or like one generator, then we have a one parameter parameterization of l-isogenies, which is exactly this kind of compactness that I was talking about. So when does this curve actually have genus 0? Well, this happens if and only if l-1 is a divisor of 12. So if you make this explicit, this is just for the primes 2, 3, 5, 7, and 13. There are other non-prime numbers where x0, n also has genus 0, but again, we will be looking at prime degrees mainly. So in this case, one can actually make this generator explicit. This is given by the function that I've described here. So we take L to the S, and then we take the quotient of the eta function evaluated at tau divided by the eta function evaluated just at tau, and take this quotient to the power 2s, where s is the quotient of 12 by l-1, and eta tau is the dedicant eta function. I can also show you the definition of this after the talk if you are interested. Importantly, now we have this parameter, so now we can actually, again, just define a polynomial. Namely, we take this FL tau, which generates this function field of x0l, and we look at its minimal polynomial over the function field generated by j tau. And this is the so-called canonical modular polynomial, and luckily, it again turns out to have coefficients in the integers. What we first want to understand is what the degrees of this polynomial actually are, because now we can again consider it as a bivariate polynomial. And to understand its degrees, we look again at the geometric setting. So we have this degree l+1 map from x0l down to x1. And now if we apply function fields, then this turns into the inclusion that we know. And of course, this function field is now just generated by FL tau, but of course, then it's also generated by FL tau and j tau. And so we get 2 function field extensions, if you want, namely of degree l+1 on the left and of degree 1 on the right. And this being degree L plus 1 on the left is exactly the statement that in the t variable, we have degree L plus 1 because it's the minimal polynomial. And on the right, we see that this exactly means that this has degree 1 because FL tau alone already generates the whole function field. So that's good. Now, to understand how this relates to l-isogenies, we kind of need to understand the relation between j tau and jl tau a bit better via the so-called Fricke involution. What we do for this is we look at another matrix, namely the matrix 0, -1, L0, and we act on this, we use this matrix to act by Möbius transformations on x0, L, and this will actually give an involution, which you can check either by squaring the matrix and seeing that it results in, I think, the diagonal matrix with entries -L on the diagonal, or you can also apply the transformation law on the right twice and see that you get back tau. So we have this involution on x0, L, but how does this actually relate to j-invariants or to isogenies? For this, we can simply look at these j-invariants j tau and jl tau, and we see that on j tau, acting by this omega L, this Fricke involution. By the way, this is also called an Atkin-Lehner involution, so sometimes maybe I will say this instead, but I mean the same involution here. If we act by this, then one can check via properties of the j-invariant that one just obtains jl tau. And since it's an involution, we immediately see that then applying it to jl tau gives us j tau again. So in terms of these two modular functions, it just switches them. It acts like a transposition of these two functions. And if you recall what these functions mean in terms of l-isogenies, then from this we see that this Fricke involution just corresponds to taking the dual of the l-isogenies that are parameterized by x0, L. So the nice thing is, if we understand that this omega L corresponds to taking the dual, then we can understand how this FL tau that we have corresponds to l-isogenies, or how it's used to detect l-isogenies if we look at the action of omega L on it. Explicitly, if we apply this omega L to FL tau, again by a precomposition, then just using properties of the definition, essentially, we can see that this is exactly the same as L to the S over FL tau. And why does this actually tell us something? The trick behind this dualization is that the j-invariant of the dual isogeny is just the j-invariant of the target of the isogeny is just the same as the j-invariant of the domain of the dual isogeny. And since the j tau function gives us the j-invariant of the domain isogeny, we can look at what omega L does and then again look at the j function to also get the target j-invariant. And so seeing how FL relates to both is exactly the key of understanding how l-isogenies are encoded. Explicitly, what this means is if we look at an l-isogeny that is parameterized by such an FL tau 0, and we reconsider the action of this omega L, then we see that the pair FL tau 0 and J0 has to give a pair of points at which the canonical modular polynomial vanishes. And additionally, this L to the S over FL tau 0, together with J1, with the target j-invariant, also have to give a pair of points at which the canonical modular polynomial vanishes. And this is exactly the kind of understanding that we wanted to get of how this FL tau relates to the l-isogenies over the complex numbers. Because now, abstracting this a bit, what we see is that the canonical modular polynomial evaluated at J0 and the canonical modular polynomial evaluated at this rational function L to the S over T and J1, these two rational functions share roots according exactly to the l-isogenies between J0 and J1. So something somehow sharing roots exactly according to the l-isogenies gives a very good candidate of something related to the classical modular polynomial. So what we can do now is we can just plug this into the resultant. Well, almost. The thing is, of course, the second function that we're looking at is not a polynomial yet, but a rational function. So what we want to do is we want to rescale it to be a polynomial by multiplying it with a suitable power of the variable. And we can also divide out the L to the S to get an integer polynomial with a monic, with a highest coefficient 1, so a monic integer polynomial. And once we have done this, then we can compute the resultant, and we see that this is actually just a classical modular polynomial up to the sign and up to a power of this degree L. And then we have successfully applied our resultant technique. So now we can just reap the rewards. And this is what I like to call the canonical multiplicity theorem. So we start with our setup. We have one of these 5 primes. We take our S to be 12 divided by L minus 1, a prime P that is not equal to L, and 2 j-invariants over FP bar. And then what our resultant theorem from earlier says is that we can count the number of l-isogenies from J0 to J1 by just counting the roots of the canonical modular polynomial evaluated at the starting j-invariant J0, where we only look at roots such that evaluating at L to the S over F and the target j-invariant J1 also results in 0. Now, we have this equality of these cardinalities, where again the right side can be a multiset. And of course, one might wonder, well, can we kind of make this into an explicit correspondence? And the answer to that is kind of. So as long as we stay away from problematic points, as I will call them here, so in this case, this will be j equal to 0 and j0 equal to 1728, then the right side will actually not be a multiset, but a proper set. So there will be no roots of higher multiplicity than 1. And then one can explicitly associate 2 roots of this canonical modular polynomial and kernel polynomial for a elliptic curve that one can also define via a generic formula. And this curve will have j-invariant J0, and the target of the isogeny defined by this kernel polynomial will have j-invariant J1. So this will really encode an l-isogeny from J0 to J1. So this is the canonical modular polynomial, but there are also 2 other ones that we want to look at. And the next will be the Atkin modular polynomial. What we can do now is we have this Fricke involution. So we can just quotient out by this, which essentially means that we still look at l-isogenies, but now only up to identifying them with their dual. And when this curve has genus 0, its function field will still be generated by a single function. Notably, however, this will not be a modular curve anymore because it's not given by a congruent subgroup of SL2 set. But that doesn't, of course, prohibit us from trying to work with this curve. So when does this curve actually have genus 0? This happens for the so-called supersingular primes. There's the list of the 15 of them from 2 to 71 with some exceptions. And the reason why they're called supersingular primes is because these are exactly the primes which all supersingular j-invariants are defined over the field FL instead of FL squared. But that's kind of as an aside. For these 15 primes, one can find a nice, I will call it here, invariant function. So one will get some modular function, which is invariant with respect to this Fricke involution. And this will correspond to a generator of the subfield of the subfunction field of x0 plus L inside the function field of x0 L. This can compute is done via a algorithm due to Atkin, but I won't give the formulas here. But once we have this so-called Atkin modular function, we can again do the same thing. We can define its minimal polynomial over the function field of x1. And this is the so-called Atkin modular polynomial this time around. And luckily, again, this will have integer coefficients. So we can again consider it as a polynomial over the integers in 2 variables, and we again want to understand its degree. So we look at the geometric picture. Here we have the degree L plus 1 map again to x1 from x0 L, but quotienting out this involution also gives us the degree 2 map from x0 L to x0 plus L. And if we apply function fields, then this reverses the maps and gets us inclusions. And this time we get the function field above generated by j tau and gl tau. To the right, we get the function field just generated by gl tau. And again, to the left, we have the field generated by j tau. And then we see on the left, this is again this degree L plus 1 thing. So we again have to have degree L plus 1 on the left. And on the right, we see actually, because the polynomial is monic in J as well, this will actually be the minimal polynomial of J over this field generated by GL tau. So this will have degree 2 in the other variable as well, because it serves as the minimal polynomial here. So since we chose our GL tau to be invariant under this Fricke involution, we can now directly understand how this GL tau actually parameterizes pairs of dual l-isogenies in this case. So if we take a GL tau 0 that parameterizes such a pair, then the Atkin modular polynomial needs to vanish at GL tau 0 evaluated at J0 as well. And also, if we plug in as a second component the target or the other j-invariant J1. So again, we have an understanding of l-isogenies in terms of polynomials, namely explicitly, if we look at these polynomials, just plugging in j0 and j1 into the second component, then these two share common roots according to these dual pairs of l-isogenies between j0 and j1. Given that, one might wonder, well, okay, can we just apply the resultant and get back the classical modular polynomial? And this will almost be true, but there is one glaring weakness that we need to pay attention to. Namely, if we specify the same j-invariant, so picking j0 and j1 to be equal, then we see that the left side will be 2 degree l+1 polynomials that coincide completely, so they have l+1 roots in common. While on the right side, we can't guarantee that we actually have any root in common. So to fix this, and this is actually what then gives the right equation, is we need to add a factor of j1 minus j0 to this power l+1 to account for these l+1 roots that we get by taking the sum polynomial. And now, just using basic properties of resultants, what one can do instead is one can replace the second polynomial by the difference quotient with the first one. And then it turns out that this will actually give just the classical modular polynomial. So we get a much cleaner resultant equation this way. So now we have achieved this resultant equation. So let's reap our rewards. Again, we start with one of these 15 supersingular primes and a characteristic that is not equal to L. And we just, for ease of notation, define this difference quotient as delta L. Then what we get just from our theorem before is that if we take any p that is not equal to L and any two j-invariants in fp bar, then the number of l-isogenies will correspond to roots of this Atkin modular polynomial, such that this difference quotient modular polynomial, where we plug in the target and the starting j-invariant, and this g will be 0. Now, similar to the canonical setting, one might wonder, well, can we make this explicit? And the answer is yes, with an asterisk. So again, we need to avoid problematic points, this being j equals 0, j equals 1, 7 to 8. In this case, for both the starting and target chain variant, one needs to be a bit careful here. And importantly, also, we need to avoid non-equivalent dual loops because they are encoded by the same root, just with multiplicity 2. And then one can actually explicitly associate to such a root of this Atkin modular polynomial an l-isogeny kernel polynomial again. And this will, of course, give an l-isogeny of between these chain variants. So now one needs to specify kind of which chain variant one wants to start from. The can has the asterisk here that these equations are a bit hard to compute and get quite unwieldy. But theoretically, it's possible. Just practically, it's a bit difficult. All right. So the first thing is we can look at the Weber modular polynomials. And this will be a bit less precise because going into details of how this is defined is mostly just technical. But what it comes down to is we have a modular curve of level 48 and genus 0. And in terms of the function field, we can give this quite explicitly by saying a generator of its function field is just given by the so-called Weber function, f of tau, which is defined, can be defined, for example, by taking eta tau squared divided by eta of tau halves times eta 2 tau. And we get a degree 72 map, or a degree 72 cover of a curve x1, which is given by this polynomial, which I will call psi w. So this is just f to the 24 minus 16 cubed, and then subtracting j times f to the 24, which means equivalently, we can represent the j-invariant via this rational function in our f. And so this degree 72 cover being given by this polynomial means that if we plug in f tau on the right, then we get j tau on the left. How can we now use this for l-isogenies? Well, the idea is that as long as we start with L at least 5, we can just take the pullback of these two curves alongside these maps to x1 to essentially work with them the same way we work with the classical modular polynomial. So what this means is that the function field of this intersection of this modular curve given by this intersection of w and gamma 0L is just given by the f Weber function in tau and in L tau. And one small remark here is one needs to take L at least 5 because the levels of the two curves need to be co-prime for this to actually work out, because we need to gamma 0L and W together, we need to generate the whole SL2 set. So this doesn't happen if L is equal to 2 or 3. But for L greater than or equal to 5, we can do this. And then we again have these two functions. So we can again just define a minimal polynomial. So we take this second function FL tau and look at its minimal polynomial over the function field generated by F tau. And this is then the so-called Weber modular polynomial. And again, by luck, or there is some reason behind this, of course, but again, essentially for the same reason as the classical modular polynomial, this again turns out to have integer coefficients. So we have this polynomial, and if we now consider it as a bivariate polynomial, then it behaves just like the classical modular polynomial in a sense. So what I mean by this is it's again symmetric, and again, it will have degree L+1 in each of the variables. Now, you might wonder, well, if this is essentially just the same as the classical modular polynomial, then why are we even looking at this? And the motivation for this really comes from point counting originally, I would say, where these polynomials were used for the SEA algorithm, so the Schuf-Elkies-Atkin algorithm, for point counting. And the reason why these polynomials are used for this is because they are much sparser and much smaller than the classical modular polynomials. So you can actually compute them for higher degrees L, for example. So we have these polynomials. Again, we want to understand how to work with l-isogenies here, because essentially, at the end, we want to still work with our j-invariants. And for this, we kind of note that by the way we constructed this polynomial, we expect it to behave just like the classical modular polynomial, but now on the level of f invariants instead of j-invariants. What this means in a bit more explicit formulation is if we look at the Weber modular polynomial in these two variables f0 and f1, and we look at the classical modular polynomial where we represent the j-invariants by these j functions of the f variables, then these two polynomials should be closely related. And this is again enough to get a resultant equation. So this is probably the most technical resultant equation that you will see here. But what it is telling us is that if we look at the Weber modular polynomial and we look at f1s that lie above some j1, then essentially this is the same as looking at the classical modular polynomial, where we look at j0s that lie below some f0. How does this now translate into a usable equation? Well, we can simplify the right side just by basic properties of the resultant. And we see that this resultant equation on the left side gives us just up to a power of this f0, the classical modular polynomial, where we represent the j-invariant j0 as this rational function of f0. And again, we have done enough work to apply our resultant technique, so we get the result that we want. We start with a prime L that's at least 5. We again take some P that's not equal to L and two j-invariants on FP bar. And now, importantly, to work on the level of these F invariants, we need to start by fixing one lift of J0 to F0. So we take one F0 such that this Weber relation, if you want to call it that, is psi W evaluates to 0 at F0 J0. Then what our statement tells us is that the number of l-isogenies from J0 to J1, where of course now J0 can be represented as this J function in F0, is just equal to the cardinality of the multiset, where we take the roots f1 of this Weber modular polynomial, but only looking at roots that lift this j-invariant J1 that we want to look at l-isogenies to. So in this way, we have kind of simplified this from the level of j-invariants to the level of f-invariants, but we need to start with one lift to actually work on the level of f-invariants. Okay, so this is the third kind of way we can apply our resultant technique. And in a sense, the sparseness of these Weber modular polynomials is exactly this kind of redundancy that we were able to remove this way. So now we want to look at how to actually apply this. For this, I want to give a brief overview of how to encode isogeny paths again. So using the classical modular polynomial, we just take a chain of j-invariants. And basically, we'd have to check that adjacent j-invariants evaluate pairwise to 0 via the classical modular polynomial. If we instead want to apply the canonical modular polynomial, then we can take a chain of these f-invariants. Here we have to check that the starting j-invariants are correct, so that we want to encode via this canonical modular polynomial without modification. And then we need to check that the target j-invariants are correct by applying this modified equation. And if we are only given the f invariants, basically what we need to check is that we have consistency from the target of f0 to the domain of f1 and so on, and that the j0 and the jk that we will obtain at the end will actually be the correct ones that are given as public parameters that we want to prove a path between. If we, instead of the canonical modular polynomials, want to apply the Atkin modular polynomials, then it looks like this. We have just a chain of these j-invariants, and we need to make sure that this j-invariant, evaluating at this j-invariant, the Atkin modular polynomial gives us the degree 2 polynomial in J, and the two roots of this polynomial that we obtain should be exactly the two j-invariants that G0 connects via a pair of dual isogenies. So we need to check, for example, that evaluating at G0 factors into J minus J0 times J minus J1, and so on for the whole chain of j-invariants. Finally, for the Weber invariants, what we do is we encode our l-isogeny path via a lifted chain of invariants. So what this should satisfy is, of course, on the level of f invariants, this should satisfy the Weber modular polynomial stepwise, and it should lift via this Weber relation the j-invariant chain that we're looking at. But of course, in a proof of knowledge, we are only given the starting and the target j-invariant as public parameters, so we can kind of forget about this middle step. And what we only need to do is we need to initially lift the first j-invariant to an f invariant. Then we can walk in the setting of f invariants, and then at the end we need to confirm that the last f invariant that we obtain actually projects down to the j-invariant that we want to reach again. So we have encoded isogeny paths with these different modular polynomials. How can we actually use this for a proof of knowledge? I won't go into much detail here, but I will give you kind of a 3-step recipe. The first is that once we have these equations, we phrase them stepwise into a so-called rank 1 constraint system, which is given by these three matrices A, B, C, and this kind of variable vector set. And what we need to do is we need to take the two matrix vector products on the left and then take the entry-wise product and check that it's equal to the matrix vector product on the right. And once we have done this and rephrased our system that way, we can just apply a rank 1 constraint system compatible zero knowledge snark, two examples being Aurora and Gero. And we just plug this in, and this gives us a zero knowledge proof of knowledge, which will be both compact and efficient. So essentially, the third step is just that we have profited from all of this. But there is one important thing to note, namely, we say that this is a rank 1 constraint system over a field. And to understand over which field we are actually working, we need to note that at least in the setting that we're interested in, namely once we start with a supersingular j-invariant and walk in a supersingular isogeny graph, all of these other types of invariants that we were looking at, so the f invariants for the canonical modular polynomial, the g invariants for the Atkin modular polynomial, and these Weber invariants for the Weber modular polynomial or the Weber equation, these all lie in fp squared. So all of these polynomials split over fp squared, so we're always working over fp squared. So in this sense, we also don't need to modify or adjust anything from the techniques we know from the classical modular polynomial. So now that we have understood this, let's see how we can actually use these to gain something. So for this, I have brought some benchmarks for L equals 2. And using this classical modular polynomial with this rank 1 constraint system approach was an idea originally due to Konglai and Levin. And this is the first column of these two tables that I show. So we see the prover time of about 1000 milliseconds in the first table, verified time of about 100 milliseconds, and proof size of about 200 kilobyte. And what we did with the canonical modular polynomials in the second column already improved on this quite a bit. But what we can do now with the Atkin modular polynomials, if we just compare this directly to the classical one, is we improve the timings by 50%. So we basically take half as much time, and the proof size also reduces by about 25%. And it's similar for the second table where we use Ligero instead of Aurora. So this is a pretty easy way how one can use these modular polynomials to obtain proofs of knowledge. And again, this already gives like a quite nice improvement on the previous state of the art. Finally, I want to end with some open questions. So the first big open question, which is probably also pretty hard to answer definitively, is, are these modular polynomials that we have found until now optimal for the proof of knowledge approach? And if not, which modular polynomials will be optimal? And how do we know that we have actually reached like the most efficiency gains that we can get with this technique. The second question is a bit easier. That's the question for comparing these modular polynomial techniques to the techniques of radical isogeny formulas. And for L equals 2, there is work on this appearing at Isogeny this year, which basically ties the approach via the Atkin modular polynomials. But it would also be interesting to look at these for L larger than 2 and to see how these compete mostly with the Atkin modular polynomials and with the Weber modular polynomials. And finally, a third question, which goes back to this geometric modular function theory that I mentioned a bit earlier in the talk, is it would be interesting to see if one can prove this isogeny characterization of the classical modular polynomial over arbitrary fields in a somewhat more approachable way. And this already starts at a point where Igusa's proof, of course, is quite heavy on algebraic geometry, and it's also a bit older, of course. So it would be nice to see if one can kind of simplify this a bit or kind of make it more approachable. Because at least to me, looking at the literature, I think that a lot of people kind of take this understanding of the classical modular polynomial for granted, but don't actually understand where it comes from. And if it was possible, it would be, I think, a nice contribution to make this more approachable and to give a more kind of understandable way to see this characterization. So if you have any comments on this, I would be happy to hear them. And otherwise, of course, I'd be happy to take questions. And here you will also see a list of references that you can consult for some of the stuff I've talked about. But of course, if you want to read more or want other references, I'm also happy to give some to you. Thank you.
Thank you very much for the talk, Sebastian. Yeah, as always, you can just unmute if you want to ask a question or type it in the chat if you're shy. So maybe I can ask like in the table.
One second, I can.
You didn't give anything for this Weber polynomial?
Yes. So in this case, I didn't give anything for the Weber polynomial because we can't use them for L equals 2, because they only apply from L at least 5.
Right, yeah.
But of course, maybe a question that is interesting related to that is how do they actually perform for these L, which we can use them for? And I don't think we have explored this in complete detail, but my understanding so far is that they are about on par with the Atkin modular polynomials. Of course, the big advantage that they have is that all the other two polynomials that we looked at, the canonical ones and the Atkin ones, are limited in the number of L's that we can reach, because the biggest L we can reach so far is 71, and the Weber modular polynomials really apply to any L except 2 or 3. So this also gives us a technique for L equals 127 or something, if that's a prime. Of course, the question is this actually useful? Does anyone actually need to look at these prime degree isogenies? But it's nice to have something that works there, or should work there, at least. Yeah. And the classical modular polynomial, of course, also applies there. But compared to the classical modular polynomial, it's definitely better to take the Weber one.
Yeah, makes sense. Thanks.
Sure.
Hi, I have a small question. Sorry if I missed, I was in a call, so maybe I missed what you said. So when you use the Weber modular polynomial, it means you use the Weber invariant f. I don't remember, is it always rational, or do you need some level structure conditions for it to be rational? I guess that for super singular elliptic curve, it's okay because like there are a lot of level structure, but I was wondering for generic.
I think it's for just in a super singular setting. In general, it won't be rational. So yeah, in the general setting, you might go to larger extensions.
Okay.
Yeah, that's my understanding of it. But of course, for what we want to do, since I think also for the Atkin and the canonical one, we're also leaving FP squared. So we're also not rational in that sense anymore, even if the j-invariants are. So this is really restricted to the super singular points being defined over FP squared.
Thanks.
Sure.
Are there any other questions? . Okay, I have a question, which is
Yes.
my favorite question to ask to any presentation, it seems. But have you looked at this in dimension 2? Like, because I know that the modular polynomials are, well, I don't even know if they're really defined in some way, because you have products and Jacobians and stuff. I don't really know what it looks like in dimension 2.
I think
But
you can.
does this theory extend to that case, or is it?
I think you can work with the Igusa invariants there, right? And there are equations there. I don't know much about it, I have to admit. They are quite unwieldy, I think. Like you have this analogous thing to the classical modular polynomial basically there. I don't think there's yet any, or at least I don't know of work that kind of tries to do like similar things to these canonical or Atkin modular polynomials there. I'm not even sure if it's possible. I would assume that there probably is something that can be done there, but I don't think this has been explored much yet. And yeah, in terms of these, of course, you could try to take these classical modular polynomials for these Igusa invariants and do a proof of knowledge that way. That should also work. It's probably not going to be very efficient though. And I think there is other work that I have heard about that instead tries to approach this via theta coordinates, for example. And I think this should be quite a bit more efficient than taking the classical modular or like the analogous thing of the classical modular polynomials at least.
So if you use if you parameterize using the Isogeny Club invariant, does everything break down if, like, what does it look like to parameterize l-isogenies to a product? Does that not capture that information, or?
Ooh. I have to admit, I don't know that.
Yeah.
I haven't looked into that enough to give a definitive answer on that. Sorry.
No worries.
I'm not.
A very open question.
No, it's fair. It's fair. It's definitely an interesting question. I just don't have that much knowledge about higher dimensional stuff yet, especially related to how this works with the equations.
Okay, thank you. Are there any other questions?
In the meantime, maybe I can show one more thing, which is quite nice. Just kind of as an extra, and I guess also to have it for people that want to watch the recording. There is a nice thing here that in the case where both x0L and x0 plus L have genus 0, one has, of course, both this FL tau and this GL tau. And one might wonder, well, how they're related. And of course, GL tau is a rational function in the function field of x0L, so it's somehow a rational expression of this FL tau. And kind of just by a very simple approach of doing some arithmetic with the polynomials, one can actually compute this representation of GL tau in terms of this FL tau explicitly via this formula that we see at the bottom. And the nice thing also, or the thing that should be expected, is that this expression is invariant if we, instead of FL tau, plug in L to the S over FL tau, which makes sense because that's exactly like taking the dual first and then kind of projecting down to this x0 plus curve. And this should give the same result as just directly projecting down because we are quotienting out this involution. So it's kind of nice that one can make this representation here explicit, just as an aside. Maybe that's interesting to someone.
We have a question in the chat. How would you find other candidates for other modular polynomials that could be interesting?
That's a very good question. I'd say it's pretty hard. So you definitely have to start from finding other congruent subgroups that would be interesting, like taking some group between gamma n and SL2Z and seeing how it relates to isogenies. And then trying to see, okay, how can you get a modular function with respect to that group that you have defined? This is not trivial at all. You probably want to play around a bit with these eta functions, for example, but again, this is just, I think, a lot of experimentation. And then I think you can make some modifications to try to see if you can reach something with integer coefficients. But I think that's also not super obvious. It's more so like it turns out to be the case, and then you can prove it instead of like saying, okay, we can see just by the way we constructed it immediately that this will have integer coefficients. That's at least my understanding of it. So a lot of this really comes down to like experimentation. And I think this also kind of shows in the Weber modular polynomials, or better in the Weber invariants, because in a sense, these are kind of the up to now most optimal removal of redundancy, if you want to call it that, of the j-invariants. But it's not clear that this is actually the optimum that can be reached, in the sense that there is still some room that could be where one could have improvements in terms of how much it can be reduced. It's just that one doesn't know if this gap that is still there is just there because the proof techniques aren't strong enough, or because we haven't found a better thing than the Weber invariants and the Weber polynomials yet, or what exactly is happening there. So to make a long answer short again, it's a lot of experimentation once you leave the setting of looking at the right modular groups. I hope that kind of answers the question, but in a sense, the more academic answer is look at stuff that other people have done over the complex numbers already. And there's a lot of stuff to be found in the point counting literature for that. And then just try to adapt that to the setting of understanding how these actually relate to isogenies, because this is kind of hidden in there sometimes made slightly explicit, but not like completely clear. And yeah, so you can also find some inspiration from that, because the point counting people have already tried to optimize their point counting algorithms quite a bit.
Okay. Thank you. Any final
Thank you for the
question?
question.
If not, then thank you, Sebastian, again for your talk.
Thank you very much.
Yeah,
Thank you for the opportunity.
Of course. So in 2 weeks, we'll be back for another episode, and Marius Ardal will be giving the talk. I probably butchered that, but yeah, we'll be giving the talk. And we hope to see you all there in 2 weeks. So thank you, everyone.
See you in 2 weeks.